Okay, can you see my screen?
Yeah, we can.
Yes. All right, great. So first of all, let me thank all the organizers for inviting me. I'm very happy to be here in this fantastic workshop, especially to talk after Professor Stefano and his very interesting talk. So in my talk, I will describe this geometric variable strain approach for soft robot modeling. I will show the theory and also some application of this approach. So in a nutshell, what we want to do with this geometric variable strain approach, we are all familiar with rigid body modeling of robot. As Stefano actually said, we can parameterize it using the joint coordinate. And this produces, as we know, a minimal set of ordinary differential equations in the standard Lagrange matrix form. This kind of model is very useful because of the collocation of actuators, sensors, and degrees of freedom. They are all located at the joint. And this makes it suitable for design, analysis, control, other than simulation. Now, we want to extend this kind of approach for hybrid soft rigid robots. And the main idea here is to see a soft link as a distributed joint, indeed. So this idea allows you to parameterize the soft link with a finite set of strain modes, which again inherit all the nice properties that we see that we have enjoy in the rigid robotics setting. Okay, so in this talk, I will present you the theoretical framework for this approach, and then I will show some recent computational way of solving the equation we produce. Then I will show some numerical test and example, and then I will move to some application to some specific case where we will exploit the collocation of actuation and coordinate. I will show you some simple extension to closed chain system and also an initial extension to nested rod system that presents some specific challenge. Here you can see some reference for the theoretical part if you are interested in what you will see. Okay, so let's consider a hybrid soft rigid system, such as this one here in this picture. So the configuration of a link with respect to the predecessor link in the chain can be defined as a curve, g of x in the special Euclidean group, that, as we know, can be represented by homogeneous matrix like that. Now, the first very important cue to highlight is that this curve is clearly a good choice for soft link, because then you parameterize your curve with respect to x. X is the curvilinear abscissa that identify the cross-section of your link. 0 is the base and L is the tip of your soft link. But at the same time, thanks to a nice analogy, this curve can be also applied to rigid link. How? So we consider x moving from 0 to 1, where 0 represents your rigid body in the reference configuration, and 1 is the actual configuration of your rigid body, let's say after the motion through your joint. And so you can imagine this set of virtual rigid body that have the same role of the cross-section. Of course, those are virtual bodies, they don't participate in the energy, but geometrically it's useful to consider this because it makes this definition of the configuration valid for every link in the system, rigid or soft. Now, once we have defined the configuration, we can take the time derivative, partial time derivative, in order to define the relative velocity twist, which is composed by the relative angular velocity and relative linear velocity. Similarly, you can take the partial space derivative with respect to x, and you define an equivalent strain twist, which is equivalent to the velocity twist, composed by an angular strain and a linear strain. And those quantities lives in the Lie algebra of the special Euclidean group. Now, we need to define coordinates for this configuration. How we do it? We notice that this is a matrix differential equation that can be formally integrated in space. So once we do that, we can do it with the exponential map in SC3 that is reported here. Now, in the case of the rigid link, your strain is nothing else than the joint skew itself. And so this strain is constant in your virtual material field, and then you can simply apply the exponential to this constant field, Xi. In the case of a soft link, the strain is not constant in general with X, and so formally you need to use the Magnus expansion in order to integrate this matrix differential equation. The Magnus expansion is an infinite series of the strain in this case, and its integral and the Lie parentheses of those, Lie bracket. And I will show you a little bit more about the Magnus expansion later. Now that the configuration and the coordinate for the configuration has been defined, we can seek a relation between the time derivative of the strain and the link velocity and acceleration. To do that, we start with the mixed partial derivative of the configuration with respect to time and space, and we obtain the transpositional relation, very important one, because they relate the space derivative of velocity and acceleration, relative velocity and relative acceleration, with the time derivative of the strain. And those are additional elements that are there because of it's not flat. The space of coordinate here is not flat. Once again, those transpositional relations can be integrated in space. They are matrix differential equations, so they can be formally integrated. And this is the result of the integration, which is our differential kinematics, because it connects, again, the relative velocity and the relative acceleration with the time derivative of your coordinate, the strain. Okay, this general differential kinematics is applicable for everything. In particular, in this general form, it's valid for soft link, but also multidimensional lumped joint. In this case, the strain is constant, as we see before. So there will be some additional simplification here that I will show you later. But anyway, this general form is valid for these two. Now, let's recover the classical one-dimensional case. So for one-dimensional joint, it ends up that those relations are flat. So all of this part, or exact if you want, all of this part disappear. And then we recover the standard relation between the joint twist and the relative velocity between two bodies, and similarly for the acceleration, the one that we usually use in rigid robotics. I think this is a nice picture that connects together some of the idea here. All right, let's now come back to our variable strain field for the general soft link case. In order to parameterize this variable strain link, we use a finite basis of strain mode represented by this matrix, big C. So the strain is parameterized with this basis. This define our generalized coordinate. And this C star is the strain of the soft link in the reference unstressed configuration, unloaded configuration, so without elastic energy. Now we can insert this relation into our differential kinematics. And what we notice is that taking the time derivative here, we can pull out Q dot, which does not depend on X. Then we can, those are relative velocities and relative acceleration. We can sum all of these relative velocity and relative acceleration all together to obtain the absolute velocity and absolute acceleration of a link, which define the geometric Jacobian and its time derivative through those integrals here that are the main ingredient of this formulation. And I will show you later how to compute actually those integrals. Okay, now that we have differential kinematics and the Jacobian, we can move to dynamics. We start with the free dynamics of rigid and soft link. For a rigid link, we can use the Newton-Euler equation. Here is the inertia terms and the joint force that are transmitted through the joint. Those are all actuation force, but also constraint force that are transmitted through the joint, and external force. For our soft link, we can use the Kosserath-Rode PDEs, which indeed use rigid and geometrically exact cross-section, which means in this PDE continuous dynamic, it is so the cross-section can have a finite deformation and finite rotation. And I would like to highlight the similarity with the Newton-Euler equation. Here you have the inertia term, the joint force act through the boundaries, so in the boundary condition of the system. Here you have the internal forces and the distributed external forces. So for what concerns the internal forces, there is an elasticity part that can be modeled with any constitutive equation. In this slide, I reported a simple Hooke linear constitutive equation. But it's also very important to notice that you can model trade-like actuations such as cable or internal McKibben actuator in the same formulation, only looking at the distance d that the other actuator have with respect to the midline. So this is a very simple way to model internal actuator. Okay, now that we have the free dynamics and the Jacobian, we can project through D'Alembert principle and obtain the generalized dynamic equilibrium in the standard Lagrangian form through virtual work, basically, where your virtual displacement needs to satisfy your joint constraint. Those are the metrics of the Lagrange equation: mass matrix, Coriolis matrix, stiffness matrix, actuation matrix, and external force. It still remains the problem to compute those metrics in the soft case. In the rigid case, we just need to remove the integral and replace the data of the problem with the lumped counterpart. But in the soft case, we still have to see how to compute those integrals. And this is the computational approach that I would like to show you now. So let's start with the constant strain case that allow us to introduce some important concepts that will be useful also for the general variable strain case. So assuming constant strain, the Magnus expansion take a very simple analytical form, which is basically the Magnus expansion is the strain itself, which is constant. And this is exactly what we have used for the rigid case, where x was equal to 1. Now, the consequence on the differential kinematic is that not only you can pull out the strain from your integral, but also you can express the adjoint with this form, exponential of the adjoint operator, which is also the tangent operator of the exponential map that is reported here. So we have now an analytical formulation for the relative velocity. Similarly, it can be done for the relative acceleration by using the derivative of the time of the tangent operator of the exponential map. So in conclusion, for the constant strain case, we have an analytic formulation for the configuration, the Jacobian, its time derivative, and by consequence, all the Lagrangian matrix can be analytically computed in principle. Now let's save this result and come back to the general variable strain case. So this first idea one can have is to use a Gaussian quadrature in order to compute the Lagrangian matrix of the model. To do so, we need to compute the value of the configuration, Jacobian matrix, and its time derivative at each of the quadrature points. So let's start with the configuration. What we use, the main ingredient here for this computational approach is the Zanna collocation approach, which is nothing else than a way to approximate the Magnus expansion at any order. For instance, here I reported a 4-order approximation of the Magnus expansion that use only 2 values of the strain in an interval. So we do that for each of the interval between a quadrature point, and this allows us to obtain a product of exponential formula to compute the configuration climbing up the chain. Furthermore, we notice that this quantity, gamma over h, where h is the length, let's say, of an interval, behave as a constant strain in each interval. So we can again use the analytic differential kinematics that we use for the constant strain case. To do so, we need to take the time derivative of the approximated Magnus expansion. Here, for example, is a 4-order one. And then we can apply the constant strain formula at each of those intervals, where now this relative velocity and relative acceleration are with respect to the precedent Gaussian quadrature point. And this allows to obtain a recursive formula for the Jacobian, again, climbing up the chain, and also its time derivative. So in conclusion, we have used a 2-level nested quadrature scheme, one for the Zanna approach in each of the interval, and one for the full link to compute the Lagrangian matrix. Okay, let's see now some numerical test and example. In this first test, we use 5 bending strains, so 5 degrees of freedom only, to model the steep follower force. Here we have a force which is pushing with at increasing strength this 100-meter long beam. So we are stressing a little bit the model. We obtain, so we follow the tip trajectory and we obtain exactly the same solution one can obtain with geometrically exact finite element method, but with only 5 degrees of freedom instead of, I don't know how many you need with a finite element method approach. In this other test, we are simulating an undamped cantilever being falling under gravity with only 4 degrees of freedom, so 4 strain mode. maybe I forgot to mention that I am using here monomial, so 1x, x squared, and x cubed, basically. So those are the basis for my strain, but one can use any kind of modes. And in fact, indeed, we observe that the energy is perfectly preserved during the simulation. Let's now look at some other example. Here you have a cable-driven actuated manipulator with this strange cable path inside and very high deformation. Here you have a hybrid soft rigid chain where the revolute joint at the base is actuated in position, in this case, where for the cable here we actuate with the tension of the cable. And finally, here you have an underwater soft robot that propels itself, again, actuating the motor in rotational input. So we have developed a matter toolbox out of this computational approach and out of this theory. Here you can see my student Iklas Ben Mida presenting how this toolbox can be used. It's very straightforward to use. There are all of these pop-up questions to set geometrical property, to set the number of Gaussian points you want to use. You can set the order of approximation for each of the strain. You can select which strain to activate or not. You can do static analysis, dynamic analysis, and so on. So, and you can find this video on YouTube and in this link from the Hamlin Symposium. So let's now see how we can exploit co-location of actuation and coordinate thanks to this model. Let's consider the static equilibrium of an actuated manipulator without external force for simplicity. So there is a clever choice of strain basis that can be made that simplify the static equilibrium and make it minimal number of degrees of freedom. So indeed, if we use the basis of the actuator itself in order to define the strain, the statics reduce to the simplest possible Q equal to U, where U is your input. And then fitting this into the reconstruction equation for the strain, we obtain this very simple yet accurate relation between your input, for instance, the tension of your cable could be, and the strain at each x. I think this is a very useful and simple formula that can be exploited for control and design. We have compared this simple formula against a more general prescribed basis and against ODE solver that can be used in this case. We consider first a cylindrical manipulator with linear and helical path, which means that your distance d has a affine or sinusoidal coordinate in local frame. And in this case, the three model match perfectly, and we have used as prescribed base, we have used affine and sinusoidal strain bases that resemble basically again the coordinate of the actuator itself. Moving to a conical case, we have kept the prescribed basis again affine and sinusoidal, ignoring the fact that the conical shape will introduce additional modes. In fact, in this case, the prescribed basis deviates significantly from the other two cases, while the simplest actuator-dependent strain basis match perfectly with the ODE solver. Okay, I will show you now a simple extension to closed chain system applied to a fin ray finger. So let's consider here a hybrid soft rigid closed chain system this time. In order to model it, we first need a basis for the constraint wrench that closed chain joint exchange between the two bodies that are connected by closed chain joint. This is potential. There are, of course, infinite bases for that. This is a potential one that is valid for general multidimensional joint as well, and use the cotangent of the exponential map. And B perpendicular here is the complement basis of the joint. In the case of one-dimensional joint, all of these expressions simplify to, and maybe you are more used to it, simplify to the complement basis alone that can serve as a basis for the constraint forces. The position constraint can be then obtained projecting the logarithm of the relative configuration between the two bodies connected by the closed chain joint for each of the closed chain joint in the system. And similarly, the velocity constraint use the Jacobian of these two connected joint. The link, sorry.
Fedrico, you still have 5 minutes left for the Q&A.
Right. Yes, thank you. I will go quicker now. So then you can start from the open chain dynamic, and you add your constraint force parameterized by the Lagrange multiplier, and then you also include in the system your constraint. Then this can be solved for the Lagrange multiplier and obtain, I think, the well-known equation for a closed chain system. Here we have applied this to a thin ray finger by validating the model in 3D and 2D, and we have used it to characterize the finger as the number of ribs and the inclination of the ribs change, and we find the optimal condition for our purpose. And then we have also prototype and test this 6-finger prototype using the optimized design. Very quickly, an interesting extension to nested rod system. What is the problem here is that so far I show you how simply we can model in thread-like actuation such as cable and McKibben actuator. However, this is not as easy for nested rod systems such as concentric tube robot or multi-backbone system, because here you have the actuator itself is not an actuator, it's part, it's really a body of the system that cannot be avoided, basically. So we want to do this extension. We start with the concentric tube robot, where the inner tube has an additional theta rotation around the center line. The approach is the same. We need to add, on top of what we've done so far, we need to add an additional degrees of freedom, additional relative velocity, and additional strain for this additional rotation. Fortunately, this is 1 degree of freedom, so the transpositional relation is exact, which simplify the Jacobian once again. Here we have parameterized again using a finite basis of strain mode for the standard degrees of standard strain plus this additional rotational strain. And then once again, we use the Jacobian to project the free static, in this case, onto the space of generalized coordinate. Note that the internal interaction force that are unknown disappear thanks to this minimal representation. And then we have used it to model a full concentric tube system, and we have compared to the shooting method, which is the most used one in the medical continuum robotics community, finding very good result. Let me just conclude with this important point. Strangely enough, the motion, the sliding of the rod has not always been ignored in this approach, and the phenomenon is known as sliding beam or spaghetti problem. Why it's a problem? Because the domain itself of your section change. So the domain grows or shrink. We don't have extension or contraction. It's the domain itself that change. So you need to add some more term in your kinematics, which this give you additional Jacobian, and in the static setting, this allows for the first time to compute the force required to control those systems. Again, I think it could be useful for control. So I think I will skip the conclusion here. I will thank my collaborator, Costanza, Anup, Iklas, and Frederic. And with that, I'm happy to take questions.
Thank you very much, Federico. Are there any questions? I already see Stefano raising their hand quickly, so go ahead.
Thank you very much, Federico, for the always interesting talk. I have, as you know, we worked in 2007 on something similar with the flexible. We discussed it previously.
Yes.
But looking at again at what you presented at the beginning, it pops up that you take time derivatives of basically element in the Lie algebra. So you take the Lagrangian approach to the modeling from the start. I wonder, I may have missed it because it was a lot of information, but I mean, don't you get problems, and maybe that'd be the reason of the spaghetti one you described, that you have inertia changes, right? If you have the more Hamiltonian approach, in which you basically use momentum rather than acceleration, then you consider the mass together, right? And then you can model it more naturally, if you wish. Because if you take the time derivative of the element in the algebra is a discussable thing, right, in a general context, because if the section are not constant inertia, you get in problems. Could you comment on that?
Yes, so we are considering here rigid cross-section. So there is no so it's a constitutive, if you want, model of the model, that the cross-section are rigid and they don't change.
Yeah, exactly. That's also, as we did in 2007, the paper you may know. But I mean, I think that if you want to extend it to sections which are not rigid, you need to go to a Hamiltonian, because the Lagrangian would fail. That's my expectation.
Thank you. I will look into that. This is indeed something I wanted to do since long. Then I find it too difficult, and I see that there were other things could be done easier.
No.
I move on that way, but I will definitely pick this up and look into it. I know about some nice formulation that somehow manage to separate somehow the cost electrodynamics and this additional degrees of freedom, if you want, that you can put on the cross section. I think in a Lagrangian point of view, you can try to add the degrees of freedom, and if you have, I mean, of course, the mass needs to be conserved. If mass goes out of the system,
you cannot go around it.
Yeah, if mass goes out of the system, then you need to have this flow out of the system, and we are starting.
But you have it, right? I mean, you have transfer. If you have not rigid, you have, obviously, due to Poisson ratio kind of effect, you have motion of mass.
Yeah, but until it doesn't go out of your system, it goes out of your local system, but maybe not out of the full system. And in any case, it's possible. For instance, I don't know if you see the screen here in this spaghetti problem. We actually also find a way to basically manage flow of mass in and out. Now here is in static setting, so we don't see all the consequence of that. But in principle, I think it could be done. Of course, you need to add this flow in the boundary, which complicate everything.
Okay. Thank you.
Thank you.
There's still one quick question from Francesco Stella. Maybe you can unmute yourself.
Yes. So thank you for the lovely speech. I really appreciated that. I would like to ask you, so if I understood correctly, the string can be described as a polynomial, right? To the order that is desired.
Yeah. Also other bases. For instance, here I use sinusoidal basis here. Depend on what I mean. This is I would say the modeling part, where really the modeler can find the best basis as user, right? The best basis to represent the system. It's a general framework, but in general, I started with the monomial, yes.
Okay, nice. So yes, the first question was like, in which cases how much should you extend this polynomial? But okay, thank you. And then I wanted to understand, okay, if you extend this polynomial, I guess also like your state will increase.
Yes.
And then for solving the static control problem that you presented, that also the control input the space of the control input has to increase accordingly or not?
So the control input here depend on the actuator, right? So this is more a design aspect of the system. Yeah, maybe here, maybe here. So you see the control input U depends on the number of actuators you have.
Yes.
Right? Q is the coefficient of your strain modes. So if you have a set of monomial, this will be the coefficient of your constant, linear, quadratic, etc. But you can take sinusoidal strain mode if it is better, Fourier transform. You can use other kind of any basis for the vector space of function at the end. Here we have function, and you can choose any basis for this vector space of function. Yeah. And this, I think, from one side, one can think about the best basis for solving a specific problem, or one can think about the best basis for controlling a specific system. And this is what I've started to think about again in this example, where this kind of strange feedback basis, I don't know how to interpret this exactly, produce a super nice static equilibrium, Q equal to U, right? Simplify drastically the problem. Another basis will not give you this simple equation. Okay. So the choice of the basis, I think it's the most important part of this approach.
So in general, yes, you choose the base so that you are able to control it with the inputs you have.
Yeah, the smarter you are with this choice, the better. Then, of course, a Lagrangian system, you can always do something with that. Whatever basis you choose, you can always, we are familiar with the Lagrangian system, so we can approach them. But if you want to optimize and find a more elegant solution, etc., you need to work on the basis, do component analysis, for instance, principal component analysis, and many things can be done. And this is, for instance, what I would like to do next.
Okay, thank you a lot.
Thank you, Francesco.
Thank you very much, Fedrico.